It's true that the Arab countries are facing several challenges, but scarcity can be common among all Arab countries, except for those who are depending mostly on desalination. But it comes to groundwater, it is a scarcity in common. Remembering the last Arab Water Council initiative, there were a number of recommendations and conclusions saying that the future of the Arab water scarcity is unconventional or depends on non-conventional water sources. And it also says that desalination needs to be several folds expanded in 2025, which is now, but that's not the case. It also says the reuse holds great potentials in most of the Arab countries, and brackish groundwater can be utilized for domestic, for irrigation, for whatever purposes with minimal treatment. But it says also that the added value for rainwater harvesting can be improved through proper management. And we are saying that a key pillar for water scarcity is the reduction of non-revenue water in the Arab world. It's true that based on this initiative, most of the countries have taken several steps, including own initiatives. They had policies, strategies, capacities, even legal frameworks, enabling environment with different structures. But the question is, which I'm raising to my colleagues in the panel, the panelists, were these initiatives and know-how coordinated among Arab countries sharing the same challenges? Are we still planning to share, to coordinate between Arab countries? But has the initiatives that you have taken has met water scarcity in the right location and right timing? These are questions that I would expect that my colleagues here will try to respond. We have 4 extinguished panelists, starting with Ms. Hiba Al-Hariri, who serves as Land and Water Officer at the FAO Regional Office for the Near East and North Africa, and she has always played a key role within the regional water scarcity initiatives. That's why we expect a response from her if that initiative that was taken by FAO has really responded to the scarcity, was really shared among all those who are in need, were initiatives in the right place at the right time with enough enabling environment wherever it was implemented. Hiba Payo is really a own one, but I would say that she is one of the key personnel in responding to the water scarcity in the region, and a key personnel in the coordination within the region as well as outside the country. Hiba will talk about, can we use desalination to respond to water scarcity in the agricultural sector? I believe limited countries have even thought of that, but the answer will be from Hiba. The floor is yours.
Do we have the pointer that changes the slides? Yeah, until they get the pointer, if we can also have the, yeah, thank you. Thank you, Mr. Moderator, for the invitation. I'm going actually to provide some insights on FAO latest assessments for unlocking the potential of desalination for agriculture in the Arab region. And I think our moderator asked a very important questions. Are we coordinating together on the required initiatives and interventions across the region? So I'm pleased to tell you that this assessment has not been officially published yet. It's going to see the light within the next couple of months. But it has been done in collaboration with the League of Arab States under the framework of FAO Regional Initiative, Water Scarcity Regional Initiative. And it was also done in collaboration with the Arab Organization of Agriculture Development and ESCWA. And the idea of this work actually came as a request from the member countries who usually attends the high-level technical committee meeting, which is the technical committee that supports the joint ministerial council between water and agriculture. And this ministerial council is convened by the League of Arab States. Every couple of years, it brings together the ministers to discuss the cross-cutting issues between water and agriculture and prioritize what are these issues that requires further assessments, maybe the development of background positioning papers on specific elements that is of interest to the region. So desalination is certainly gaining momentum as a key adaptation measure. And it is this defined by the International Panel of Climate Change, as it offers a vital supply-side solution in arid zones like the MENA region. And as we are expecting the food gap and demand to increase by around 70% by 2050, the main challenge in our region would be to provide sufficient quantitative, good quality irrigation water in a sustainable way and also in a resilient way. So the main objective, so the main objective of this assessment was to provide, it was to provide a comprehensive structured analysis on the role of desalination. We wanted to explore what were the agronomic benefits, the socioeconomic externalities, the environmental considerations, and what were also the latest technological landscape and advancements. So initially, of course, desalination started from the 50s to the 70s as a very restricted resource in islands and maybe used in military bases only. But starting the 70s, it became the main resource for cities for the Arabian Peninsula. And now it has been accepted by the State of the Gulf Collaboration Council that the future water demand for the GCC countries is going to be met through desalination. So it's no longer restricted. We have countries like Qatar relies 100% on desalination, countries like Kuwait. If we looked at the map on the upper left side, we will see that the expansion in the installed capacities of desalination around the world actually confirms the momentum of desalination and its promises. If we wanted to look at the distribution of installed capacities by use, we will find that currently desalination for agriculture only represents from 2 to 3%. But we also know that there are several countries that uses desalinized brackish water and has expanded in the use of desalinated brackish water, for example, in Spain, and now the desalination for agriculture in Spain is around 22%. Now, with respect to the number of desalination plants in the Arab region, for both planned and under construction, it is also increasing, as you can see in the figure. Some countries actually in the Arab region has also started the use of desalination for agriculture. For example, in Kuwait, with approximately 13%. Now, the launch of desalination projects in general involves several challenges and also several requirements that are needed, and it actually involves the development of comprehensive technical expertise file. And in order to identify the major requirements and also the major limitations, a survey was done in consultation with more than 23 international desalination experts from around the globe to identify the main requirements and what were the limiting factors. From the results obtained from this survey, we will see that there was a high heterogeneity of the environmental and socioeconomic requirements across the results from different experts. But with respect to key requirements, what was identified, as you can see in the figure, was the environmental impacts assessments, the need for environmental monitoring, incentive programs for financial support, also the investments in R&D, and etc. And particularly for the desalination for agriculture, key data that were identified also included information on water distribution and usages for irrigations to enhance the agriculture efficiency, as well as quantitative and qualitative aspects of resources with respect to the rainfall, the infiltration, recharge, and water quality. And the reason for that is that for desalination to be cost-effective and to be actually successful, it needs to be integrated within the integrated water resources management strategies of the countries. It cannot be taken solely as a specific intervention in one location. You need to see how desalination is going to complement the current resources, where is the best locations to complement such resources, what is the impact on the water quality and in the crops that is going to be cultivated. Now, with respect to the barrier, of course, the most common barrier was related to the cost of the produced water, which certainly require higher cost compared to the conventional resources, but still the desalinization of brackish water seems to be a good opportunity and offers also a good cost-effective disposal of brine if it was done closer to the coastal areas. Now, on speaking about some of the environmental challenges, of course, the development of desalination projects in general, they have several adverse effects on, for example, the ocean space. When we are talking about the impact of the intake, the impact of the brine discharge on aquatic ecosystems, we're also looking at impacts on on air quality and water quality, and the air quality is related to the greenhouse emissions. But the most important thing to highlight here is that with respect to the environmental regulation, we still don't have specific standards for the development of environmental impact assessments. We have actually guidelines that are developed by different countries and also by the United Nations Environmental Program, UNEP. But there is no specific standards yet agreed on, and the environmental impact assessment has not been properly incorporated within the management policies of desalination projects for agriculture, although we have available technical and management strategies that we can use to mitigate the impact, but it has not yet been used for the management policy. Now, an additional potential environmental impact that needs to be highlighted is related also to the disposal of the RO membranes. Currently, annually, we have around 14,000 tons of membranes that gets disposed worldwide. Currently, we have the incineration of membranes for thermal uses as one of the options, but this option is actually causing lots of environmental impacts. So there are lots of new researches looking at how we can provide the absolute membranes with a new life cycle that can be used in other applications that require maybe less requirements. For example, if we're talking about gray water or for example, the wastewater treatment. Now, regarding to the socioeconomic externalities, the desalination for agriculture projects, they of course have some positive and negative impacts. If we're talking about some positive impacts, we're looking at, of course, improved water security, expansion of arable land, introduction of higher value crops, and economic diversification. But from the other side, we have some negative aspects that needs to be taken into account. Some of them is related to the health dimensions. related to the water quality and its impact on the crops, which needs to be addressed. Also, the creation of a relative scarcities, if we're talking about higher costs, particularly if we're speaking about the impact on poor farmers and rural areas. That is why it is very important during the development of any feasibility studies for desalination for agriculture that we follow a comprehensive approach, taking into account the necessary economic and social aspects that must be adopted to ensure a long-term sustainability of these projects, particularly for traditional farming communities. It was also seen that generally there is a social acceptance of desalination projects normally, as this does not actually represent a limiting factor, but there are low levels of engagement with the public communities in those locations, and also low levels of contributions to the environmental standards as well that needs to be taken into account. Now, with respect to the water quality, this is also a very important concern that needs to be addressed. Now, incorporating desalinated water in agriculture have varying agronomic effects, particularly with respect to the lack of essential nutrition that needs to be addressed. Also, this would lead to higher fertilization needs, especially if we're speaking about the greenhouse crops. In addition to that, also the chemical composition of the desalinated water may also degrade the soil structure on the long term, which also requires some attention and might affect the crop yield. There are also potential toxicity with high levels of borons and chloride. Therefore, the post-treatment of the water, desalinated water, is highly needed in order to stabilize the produced water and to make it more compatible, first with the distribution network by adding corrosion inhibitor, and also to make it compatible with the end user requirements and avoid any impacts on the soil or on the crops. Now, from experience, it seems that the replacement of traditional irrigation with desalinated water is not the best option, but the mixing of the water with normal irrigated water, or also we've seen it with treated wastewater in some locations, like, for example, experiences in Malta, seem to produce much better results. The correction of application and management of specific quality regulation by mixing and management seems to be provide the best option. And also this needs to be coupled with water and soil monitoring that can mitigate the risks for agricultural irrigation with desalinated water. Sure. Now, moving maybe quickly to the impact of energy use and desalination, and maybe I'll have to run much quicker for the next couple of slides. If we're talking about the most commercially used technologies, we're speaking about RO and electrodialysis. As you can see, the energy uses in the brackish water is actually less than seawater, and which reflects on the cost. Currently, RO and electrodialysis represents the major types of technologies that are being used globally. It is also maybe good to mention that with respect to the carbon footprints, also RO has the lower CO2 emission compared to thermal desalination technologies. We're talking about 0.4 to 6.7 kilogram of CO2 per cubic meter. However, for the brackish water, the RO desalination estimated carbon footprint is around 0.4. Now, with respect to the cost in general, advancements in the membrane technologies and the energy recovery systems has certainly reduced the cost of desalination over the past 20 years. We have seen this very clear in the comparing the prices, but also it is also important to mention that the membrane, the technologies of membranes as well have provided the possibility to provide fertilizers as well through the different membrane technologies. AI also powered smart systems also contributes to the lowering of price, and also, of course, the use of solar powers and solar energy, which actually increases the potential of bringing the operational costs of the desalination plants for agriculture to be more reasonable in the future, and might be contributing more to the regular irrigation schemes in various countries. Finally, with respect to policies and strategies, as for environmental regulations, as I mentioned, there are no specific standards for environmental impact assessments, but it's also important to highlight that regardless of the environmental part, policies must also include financial incentives like grants, subsidies, and also potential collaboration with the private sector, as it has proved to be also providing promising results, and Morocco is a big example for that. Now, integrating renewable energy sources to power desalination plants also reduces the environmental impact, and implementing regulations for the safe disposal of brines, such as deep wells, and maybe prioritizing the desalination for agriculture on coastal zones where the brine disposal is much easier and is more cost effective than inland disposal. Water pricing and allocation policies are also very important, and most importantly, the investments in R&D needs to be improved, as currently the localization of desalination technologies is not really gaining the required attention, which can also contribute significantly to the cost if it was done properly and regularly through and given the proper priorities by the different governments across the region. Maybe I will stop here for the time. Thank you.
Thank you, Hiba. That was really insightful. And I'm sorry to stop you short, but for sake of time, thank you very much. Luckily, we have listed a number of challenges.
I covered mostly everything, yeah.
Almost, yes. You have listed a number of challenges and limiting factors, but the slide before, the last you said about advances in technologies, and that takes us smoothly to the next speaker. Professor Kteshat will address the emerging desalination technologies. Dr. Kteshat, we are really proud to have you here. He is the chairman of the Chemical Engineering Department at the University of Jordan, but he is also very well known in his research in desalination technologies, and he is one of the pioneers and the leading innovative specialist in desalination. I'm sure your presentation will complement what Hiba has started in terms of, are these challenges still there? Are we facing a new era where we say that desalination now is a possibility without fear of these challenges? Thank you very much. Please.
Thank you so much, Mr. Chairman, for your introduction. Just waiting for the slides to be uploaded to start my presentation, but I can start. I've worked on desalination and membrane desalination since I did my master's degree. I did my PhD in membrane desalination, and throughout my academic career, I've worked on developing innovative technologies for water desalination. Especially, I'm a specialist in membrane manufacturing and design. I will speak following maybe Ms. Hiba talk about the new uses of desalination. Actually, desalination, maybe it's the most viable option. Stuck a lot. I think that's fine. So if we look at our water resources, 97% of the water that's available on our planet is coming in terms of salty water, seawater. So it doesn't take a genius to tell you that desalination holds the key for solving the ever-bending water problem worldwide. I remember here a quote by John F. Kennedy in 1961. He stated that if we are able to achieve desalination at very low cost and more energy efficient, this accomplishment will dwarf any other scientific accomplishment because it's about the sustainability of our being on this planet. The problem with the desalination in general, it used to be two different categories. We can that includes a phase change, the oldest one, evaporation, condensation, and recovering of the water. This is called thermal processes, and the industrial shape of them is coming into two major technologies, multi-stage flash and multi-effect distillation. And in the 60s, it becomes membrane processes, and reverse osmosis was the leading in terms of these technologies. We have around more than 17,000 plants currently running in the world, producing more than 100 million cubic meter per day in 133 countries of these, that use desalination. The market size will be expected to be around $32 billion in 2025. More than 52% of these desalination plants are located in our Gulf countries. So it is one of the major consumers to desalination, and there is a lot of these, most of their water are generated by desalination. The current technologies actually, they face some challenges. One of them is the severe energy requirement. In thermal desalination, you need to heat to high temperatures. In reverse osmosis, you need to apply high pressure. The sophisticated pre-treatment requirement, and this is because, you know, like in reverse osmosis, simply there is chemical interaction between the membrane matrix and the water. So because of this interaction, there is a danger of the membrane fouling, and that's another issue. So we need, as Hiba stated, to replace these membranes frequently. There is environmental impact associated with the brine. For example, the performance ratio in reverse osmosis for seawater desalination is around 40%. That means 60% of the water that we take as a feed is disposed back as a brine, and that's another issue that we need to address in desalination. So brine management is one of the issues. The high cost of the membrane, because it's a very sophisticated knowledge, and here I need to mention this. Like last month, I was visiting Aquatic Amsterdam, and you know, like I'm a membrane manufacturing guy, so I was looking for companies who manufacture membranes. To my surprise, only 2 or 3 companies worldwide manufacture membranes, and the other companies are only doing the module thing. So the membrane, the know-how of the membrane, the sophisticated knowledge of the membrane manufacturing is one of the issues that need to be addressed in our region, to localize that technology in our region in order to be independent in our decision making when it comes to water, especially like Gulf countries, because they are highly dependent on desalination. As I've mentioned before, now I will talk about from my own experience in research and development. I will talk about what kind of new technologies that can penetrate the desalination market and solve the problems that RO cannot solve. RO, the problem with reverse osmosis when it comes to small scale, less than 1,000 cubic meter per day, the cost becomes very high, so it's not very efficient. In addition, the quality of the water, brackish water quality sometimes changing from one area to another, so that means whatever reverse osmosis can work here might not work there. We do have some, one of the examples that I faced, having heavy metals or having iron contamination or having radioactive materials that is contaminating with the water. Reverse osmosis simply cannot address these problems. So there, I have to tell you about these 3 technologies. Forward osmosis, electrochemical desalination, specifically the electrodialysis and membrane distillation. My specialty is in membrane distillation, and I will highlight the latest results that I've achieved throughout my research. The idea, all of these technologies, what we need is low carbon desalination, because they might use solar energy in a simpler way than reverse osmosis, and it can be easily integrated with the currently desalination technologies. I will just tell you how that could be achieved. The concept of forward osmosis is the opposite of reverse osmosis. In forward osmosis, what we simply do, the nature is the osmosis phenomena. So what we simply do, we design a dew solution and a membrane. This dew solution, the concentration of the salts there is much higher than the seawater, so water will start diffuse from the higher water concentration to the lower water concentration, which is the osmosis phenomena. What we need to do is a membrane. Actually, in Singapore, there is a pilot scale study that is claimed to be successful, and it produced 10 cubic meter per day using forward osmosis technology. The technology was developed by National University of Singapore recently, a couple of years ago. Another technology is the competitive advantages of forward osmosis. It can treat high salinity water up to 20% TDS. Remember, reverse osmosis cannot exceed 6%. So here you can couple forward osmosis to treat the brine of reverse osmosis, for example. The energy requirements are much lower because it doesn't require pressure. In reverse osmosis, you need to apply a pressure in order to reverse the flow of the water to be from the seawater into the fresh water. The fouling nature here, it's reversible fouling. So even if there is fouling, it could be reversible. It's not like RO. Less chemical used because you don't need post-treatment or pre-treatment. It can reject boron, which is one of the major problems that RO can face. So one of the ideal scenarios is coupling forward osmosis with reverse osmosis. But still, I'm just going to be honest, still the membrane still needs more development and fine-tuning in order to be commercially competitive with currently available technologies. Electrodialysis, the idea is simple. You know, salts are in forms of ions. That is electrically charged, positive and negative ions. So we apply a membrane anode and a membrane cathode, which can separate these salts. But the problem with these technologies, I will just mention what advantages. It is easily to tune, low pressure, life cycle cost is very good and very easy to maintain. But the problem, when you have a contaminant that is not simply ionized, so how you can separate them, because it's all about having a charge of the ions. The latest technology, and I do believe it is the most mature technology among all other technologies, is membrane distillation. Membrane distillation simply is a hybrid technology that combines both thermal and membrane. But here, the temperature that you need to heat is not boiling point. You don't need to reach 100 or 80 degrees Celsius. Maybe at 40 or 50 degrees Celsius, you can achieve desalination. The concept simply, we have a membrane that is hydrophobic by nature, so it doesn't allow liquids to go through the membrane. Only water vapor or gases can go through the membrane. When you apply a thermal gradient, this generates a chemical potential gradients between both ends of the membrane, so it can work in membrane distillation. It has 100% water purification, can treat high salinity. Professor Derioli in Italy treated water that is 58%, 58, that is double the Dead Sea with membrane distillation, and it was successful. It can be coupled with waste heat or renewable energy. Longer membrane life and no sophisticated pre-treatment is required. This is membrane distillation. Membrane distillation, one of the major ideas now is to use the brine of reverse osmosis or thermal desalination processes coupled with membrane distillation process and produce further water, and then you can even, the salt becomes as a solid waste, so that could be achieved as a zero liquid discharge brine management. The disadvantages is membrane wetting, and I wanted to show you this equation because it led me to something to do with my research. Throughout this equation, I understood that the vapor pressure on a surface that is very hydrophobic, where the contact angle is above 130, and the pore size is in nanometer, less than 2 nanometer. The model told me from Kelvin equation that the membrane, if you design such membrane with this sophistication, super hydrophobic, very small pore size that is between 0.5 and 2 nanometer, then the membrane can see the water vapor pressure, although it is at room temperature, 25 degrees Celsius, but the membrane see it as 60 degrees Celsius. So the model told me that I can desalinize water without applying a pressure driving force, not even a thermal driving force. And that was the model. So we decided, okay, now this is different pore sizes, and you can see the vapor pressure that is compared at even 25 degrees Celsius, but the vapor pressure is around 41 degrees Celsius because the membrane see this in a different way. Then I designed this membrane, manufactured this membrane by using a polymerization reaction. I call it interfacial polymerization. And what I want to show you the major results. The major results, when we used our new membrane and compare it with a commercial membrane, at 25 degrees Celsius, our flux was around 50 liter per square meter per hour at room temperature, atmospheric pressure, without heating, without applying pressure. The commercial available PTFE membranes produced no flux whatsoever. And the more you increase the temperature, of course, the flux increases. But the most important, significant result is being able to desalinize water at room temperature without applying pressure. Simply, this is my conclusive remarks. This research was published, there's 2 international patents, US patents, and 2 papers published in Nature Communication and Nature Scientific Reports. And most recently, Nature editorial board chose this research article as one of the current how local technologies could help solve worldwide problems. So it was selected by Nature editorial board because, to me, that's one of the most significant breakthroughs that I've achieved in my research so far, and I hope we can work further on the development of such membrane to be commercialized. Thank you so much.
Thank you very much. Well, Professor Tishat, you have a hope, and we also have a hope that your recommendations and conclusions are taken by policymakers. It is the time now that your work and the academia work is really translated into policies and practices on the ground. Thank you very much for this. And with both presentations on desalination, I'm sure a number of questions will be coming up soon. But this is really a hope that you are giving us on how to tackle the water scarcity in the region. Moving from desalination to wastewater. As I've said, the non-conventional water is one of the key pillars of meeting the water scarcity in the region. And the reuse has great potentials, not only for irrigation, but even for industry, for municipal purposes. So reuse is really one of the issues that all of us are looking for. Now, I'm really honored to introduce Pauline. Pauline is not only a manager, she is the manager of the Khirbet Samra wastewater treatment plant, but with her 15 years of experience, has come up with smart solutions, sustainable operations, and that is what we are looking for. We have said always that wastewater reuse requires proper management, and I'm sure you have built that management. And we are proud to say that it's time that you share these successes with the audience here. Thank you very much. Please.
Okay, thank you very much for the introduction. So I'm very pleased to participate to this session because when we talk about unconventional water resource, definitely, everybody think about desalination first, I would say, and we understand why, but there is definitely, we believe, some other opportunity, and especially on the water reuse. So definitely using the example of Samra, I will provide some insight, but also, basically showcasing some other case that Veolia is operating. clarification. Okay. No, it went too far. It's the end of the presentation. Yeah, that's the end of the presentation. So can you come back to the beginning? So basically, before we enter really in the subject of water reuse, I wanted just to remind everybody on. I think now okay, no? It's the bottom one, no? Okay, yeah, perfect. So I wanted just to remind key numbers in terms of understanding the scale of the water needs that we are talking about. So the Middle East, North Africa region, so it represents around 9% of the land world area and 6% of the world population. But we are effectively talking about only 1% of the fresh water. So as it's been, discussed a lot since the beginning of this conference, we are in the most water scarce region in the world with an average renewable water available per capita 10 times lower than the global average. So we are talking about around 550 meter cube per day per capita. So, and in this context of water scarcity, the region is also definitely subject to climate change. So we expect, especially in the region, to go even beyond than the 2%, that 2 degrees that people are always mentioning. But in the region, we expect an increase of 4%. Increase of the temperature, which definitely impacts rainfall, evaporation, and so availability of the freshwater resource. But in this context of water supply, we have, on the other hand, a very dynamic region with a growth population which is, basically around 2% per year. We are currently at around 500 million, and we expect that to reach 680 million by 2050, which is basically an increase by 50% when we look at 2015. And on top of this, it's also a very dynamic region from a perspective that it's a region which wants to enhance industrial development as well as diversifying the economy. So we are talking about a region which will need more water, despite also an increasing number of water consumption from the population itself. So in this context, for sure, desalination is one of the alternatives, and we know that in the Gulf country, for example, it's been well developed. However, we believe that also a sustainable response to this growing water demand is the water circular economy. So when we talk about water circular economy, what we think? It's moving from a linear approach where we think, okay, where I can get the water, produce potable water, and how I can get rid and not pollute the environment with the wastewater, to a circular cycle where I try to optimize basically my water need. So I'm talking about water reduction, so working on non-revenue water, working also on water consumption of people, but also then thinking about how I maximize this use. So this resource, it's instead of saying, okay, I just use it for potable water, can I use it a second time for something else? So for example, agriculture, irrigation, on industry, urban and landscaping irrigation, or even in some countries, aquifer recharge, or even production of drinking water. And then from that, also how I regenerate this resource. So as we were talking, in some countries, it can be used as aquifer recharge, so we regenerate basically the initial water resource that we need to produce potentially potable water. Okay, so maybe before. What is worth mentioning also when we talk about this circular water economy, it's also that it provides some benefit in terms of resilience of the services. Because basically we are dependent on one cycle of water, so potentially a limited input in terms of the supply, so it provides resilience. It's also improving definitely the environment and the biodiversity, because we are talking about treating basically those pollutants to remove them from the water, and so it's not going into the environment. But also water which is available for economical development and stability, social stability, and as well as while really ensuring health and security of the resource. Okay, so just a little bit maybe focusing on the region in terms of water reuse. I mean, what is the potential and what that represents in the region? So we are talking, as I was mentioning earlier, around 500 million people, so producing around 21.5 billion of meter cube of wastewater per year in the region. And currently, only 46% of this wastewater is being treated and reused. And only 10% is being directly reused. So definitely looking at that, we look at really an uncapped and growing water resource available in this big water equation. Because what is worth, I think, noting, it's really reclaimed water is the only source of water which will grow with the population and with the water use. So I think it's worth mentioning that it's not new for the region. I mean, we mentioned it a little bit earlier. It's definitely a journey that has already started and which I think is fully recognized by a number of countries in this region. A number, I would say reuse is part of almost all the national water strategy in this region. We know, let's say, for example, in Jordan, they want to increase by 60% the water, basically for reuse to represent 60% of the water supply for agriculture. In some Gulf countries, they are looking at 100% water reuse. In Egypt, 70%. So it's really already quite well engaged. However, we believe that really it needs to be accelerated because basically 25 billion of meter cube is potentially missing in 2050. And also, basically, it needs to really be accelerated. So in this journey, basically, I will present a little bit more Veolia, which is basically one of the partner in the Samra O&M company that I'm currently managing. Because basically they are the leader in water reuse. They've been, so you can see in 2023, they were recycling 1.1 billion meter cube of water. Okay, we are talking about a company with 170 years of experience and expertise, really from the feasibility study to the design and engineering with technology. So you can see with more than 43 patents, and to basically operation and services. So a company who knows basically the water cycle from the production into the reuse. Okay. So just focusing on this region, Veolia currently in the Middle East is producing 556 million of meter cube, which are recycled in 23. And so we can see in terms of reuse, we are talking mainly about agriculture. So like in Jordan, basically all the 100% of the water treated in Samra is recycled for agriculture purposes, but also for urban. So we are talking about landscaping and irrigation within cities, and also for industrials. Okay. So what is important to mention is basically Veolia is having a global approach around those 4 pillars of reuse, where they are able to really provide a support to their customer, which is tailored by the context, by the needs, and also by just the quality of water and the purpose of reuse. So they can accompany their customer and their partners from really feasibility study, design engineering, and operation and optimization of this operation. So you can see basically through, I was talking about portfolio and 43 patents. So there is really technology which are available and which can be tailored based on the purpose of water reuse. So if we talk about agriculture, we talk about high quality water, but where biological treatment with some polishing, with some filtration, and some economical disinfection is acceptable to meet the standards. When we are starting talking about urban reuse or environmental reuse, so potentially aquifer recharge, we need a little bit higher quality. So we look at often more complex tertiary treatment, which basically can provide this level of quality. And even further, with very high quality water, where we go more for advanced secondary and tertiary treatment and more complex disinfection process to make sure that really the water is safe to use. So that is just an example, basically, of the few technology which are patented by Veolia. So this company is really, Veolia has the know-how in terms of operation. I mean, operating really wastewater and water treatment site for a long time. But also in terms of technology, they have a specific know-how on specific technology. So for example, you can see on advanced biological treatment with membrane, with the ultrafiltration. If I move to more complex process, so we have the ozonation, the activated carbon, and up to the reverse osmosis with the barrel technology. So if I focus, if I now become a little bit more practical and factual in terms of presenting few use cases just to understand the situation. So as I mentioned, in Jordan, so basically they've been quite pioneer in this reuse. We can see that currently 90% of the treated water is reused in Jordan, and it represents 15% of the water resource for the country. And we can see that 80% is reused in the Jordan Valley, so really directly for agriculture. And there is this ambition to increase that even further by 80 million meter cube. And so how that has been successfully done, it's really by, I would say, a successful private-public partnership with the Samra BOT contract with the Ministry of Water and Irrigation, where basically we treat 60% of the wastewater in Jordan, 100% is recycled, and basically discharged into the Wadi, then going to the King Tala Dam, to then being able to be reused in the Jordan Valley. So basically, we are talking about biological treatment with some disinfection, and which meet 25% of the country agricultural needs. So if we move to a different type of reuse, we have also reuse, as I mentioned, for urban use, so more like landscaping, so which is quite, I would say, developed and extend in the Gulf country. So with the example of Qatar, where we operate Doha North wastewater treatment plant, and basically with an additional advanced tertiary treatment with ultrafiltration and disinfection with chlorination, we are able to provide really high quality water, which can be used basically to irrigate landscaping, garden, so public place where people can really sit and enjoy safely. But then it's going even further. So you see, I go through, the level of quality. We start with irrigation, where potentially there is constraint, but to a certain level, then to landscaping, and even we can go further. So when we start talking about industrial water, so it's a much more complex type of effluent. We know with hazardous waste, So much more complex. And Veolia with Renault in Morocco has been partnering, and really from the beginning, because they've been looking from the design of the solution until now the operation. Basically, they were having a common goal to deliver a plant with zero liquid discharge. So basically, no wasted water is going out of the site. And basically, definitely, it's a complex process, but with the know-how, etc., they are currently, first they achieved two things. First, the zero liquid discharge has been achieved, but also what is worth mentioning, it's the water consumption has been optimized. So in average, normally to produce a car, you need around 2 meters cubed of water. Now in Tanger, you need almost only 1. So it's really a combined partnership, which also highlights the flexibility in terms of how reuse can be done. It can be a private-public partnership, it can be private-private, it can be just an operation, a design. There is really an opportunity of how the solution can be put in place, I would say technically, but also financially. And then, so that was just just to show the complexity sometimes of the treatment to achieve such things. Wait, I just have a slide. Wait. Okay, and so just to finish with, I would say the uppermost water quality. It's with the example of Namibia, where in the capital of Namibia, in Windhoek, Veolia operate a plant which produce direct potable water. So basically the wastewater is collected from the city, and through a series of complex process, basically it's producing water which is used by 400,000 inhabitants in Namibia. So there is really the ability technically to produce really very high quality water from wastewater. So, I mean, it's just to highlight, we've been talking about a lot about desalination, which is definitely one of the solution. However, water reuse with the circular economy provides the opportunity, basically, to recognize that water is too precious to be only used once. Okay, thank you very much.
Thank you, Pauline. Well, just if you put what we have seen so far together, the initiative, academia innovation, and public-private partnership, just put them together and see how far we can really go in facing the water scarcity. I'm sure that the next speaker will tackle that, because Jordan has built enough experience so far, and especially when we have a specialist, Dr. Tawfiq, who's now the Assistant Secretary General for Water Basins Affairs, and he has held a number of positions, including Environment and Reuse Director, Yarmouk Basin Director, Amman Zarqa Basin Director, Engineer at the Environmental and Reuse Directorate. So he has gathered all together. The question is, these key initiatives that we have seen in Jordan, are they the response for Jordan water scarcity? Are we saying that with the implementation and incorporating these initiatives and innovations in the policies in Jordan will be somewhere else near future? Dr. Tawfiq will give us the operational experience of Jordan in both, not only wastewater, but also wastewater and rainwater harvesting. The floor is yours.
Many thanks, doctors. Okay. Excuse me, I will speak in Arabic to catch the fruit. Okay. السلام عليكم. أنا الدكتور توفيق الرحيمي، مديرية البيئة سابقا وإعادة الاستخدام، والآن حاليا أشغل مساعد الأمين العام لشؤون الأحواض المائية. وجدت الترابط العالي والتكاملية بين الأحواض المائية، المياه الجوفية، وإعادة الاستخدام. الآن راح أبدأ كمقدمة عن واقع الأردن في قصة نجاح رغم التحديات اللي احنا بنواجهها بالأردن. اوكي. زي ما تفضل زميلنا هون انه المياه تقريبا 70% احنا الناس يسموها الكرة المائية وليس الكرة الأرضية، لأنه 70% منها مياه، ولكن التحدي الكبير الموجود لنا انه 1% هو الموجود منها، 70% يستخدم لأغراض زراعية. إذا تكلمنا عن واقع الأردن في أكثر من مقالة وأكثر من مكان، نقول إحنا الأردن أفقر دولة مائية أو ثاني أفقر دولة مائية. إحنا ما نطمح له أن يكون الأردن أفضل دولة مائية في استخدام كفاءة المياه والمحافظة عليها. الآن حصة الفرد تقريبا 60 متر مكعب. هذا راح طبعا ينقص إذا استمر الوضع المائي على هذا الوضع والمصادر ومحدودية المصادر. بال 1946 كانت حصة الفرد 3600 متر مكعب، الآن بال 2025 تقريبا 60 متر مكعب المصرح عنها. يعني إذا استمر هذا الوضع على الوضع الحالي هذا، فإحنا يعني في تناقص مستمر في كمية المياه المتاحة للفرد. التحدي الكبير انه مساحه المملكه الاردنيه الهاشميه 88% من او 99% منها ديزرت، يعني مساحات ليس فيها مسطحات مائيه، تقريبا تستقبل اقل من 200 ملي او 150 ملي. فهذا تحدي عالي جدا. الان المزارع الاردني او المواطن الاردني ما شعر بالتغير المناخي، هو لمسه في كل مناحي حياته، في المناحي الاقتصاديه والاجتماعيه. المناخ يتميز بأرد أند سيمي أرد، بالصيف مرتفع درجة الحرارة وفي تبخر عالي، بالشتاء أمطار قليلة وفي تذبذب في الأمطار وكميتها. المياه الجوفية، كل الأحواض المائية الموجودة عندنا 12 حوض مائي جوفي تقريبا، يعني كلها فيها استنزاف عالي وكلها فيها دبلشن. تقريبا في حوضين الحمد والسرحان لحد الآن فيهن الأمور يعني لسه ما صار في استنزاف، ولكن باقي الأحواض كلها فيها استنزاف عالي جدا. أنا بدي أروح على يعني المشاكل والتحديات اللي إحنا بنواجهها. التحديات عميقة وكبيرة جدا، في ظروف داخلية وظروف خارجية، مصادر مائية. المصدر المائي المتاح لنا بعيد جدا عن أماكن السكن، الهجرات اللي صارت، الهجرات القصرية، المحيط الملتهب اللي إحنا موجودين فيه، كل هذه المشاكل أدت يعني النمو السكاني اللي موجود، كلها أدت إلى نقصان حصة الفرد. الآن المصادر المائية جزء شرحوا عنها زملائنا. الووتر سبلاي تقريبا مليار و100 مليون. احنا السنه هاي لحد الان جزء وصل لنا الموسم المطري 40%، يعني بمعنى انه 4 مليار او 5 مليار. حتى نقول انه ما في بلش عندنا موسم جفاف موجود، لازم يكون واصلنا 8 مليار متر مكعب بالسنه. الآن شايفين التغير المناخي كيف يعني درج علينا. الاستعمالات المياه المليار و100 مليون لاستخدام البلدية أو الشرب المنزلي والزراعة، والشيء الثاني للصناعة. التغير المناخي ملامس، يعني التغير المناخي مؤثر في جميع مناحي البيئة. شوف بس 1950 البحر الميت كيف كان اللي احنا موجودين فيه، كيف بده يصير بال 2050 إذا استمرت هذا الوضع. التصدعات اللي حصلت، التغير المناخي بالنسبة لتغير الأمطار، بالجفاف، بالزراعة، تأثيره على الإيكونوميك والسوشيال والانترنال. بدي أحكي وبدي الصورة هاي تكون موجودة، هاي صورة الدولار اللي موجود بالتواليت ترافقنا بكل سلايد. أنا بدي أحكي الآن عن قصة النجاح الموجودة بالأردن. المحطات واستغلال المياه الخارجة من المياه المعالجة من المحطات هي كنز. ليش؟ أول شيء هي دائمة لأي مشروع، إحنا إذا نبحث عن sustainable فهي دائمة. والشيء الثاني هي مستزايد. لحد الآن الاتفاقيات والزراعات اللي صارت على المحطات المجاورة، كل المياه اللي دخلت للمحطة كل سنة قاعدة بتزيد، كل سنة قاعدة تقفز أصلا بزيادة نوعية فيها. الآن تقريبا السنة هاي 2024 التقرير كانه 215 مليون متر مكعب تم معالجتها في 29 محطة. المحطات يعني كلها متوسطة إلى صغيرة. أكبر عندنا محطة هي محطة الخربة السمراء تقريبا 365 ألف متر مكعب يوميا. بدناش نحكي عن يعني بس ايش الاستخدام. الآن مكونات النفايات الموجودة بالمياه المعالجة ليس خطرة وليس يعني، بس لها تفصيلات: أجزاء نفايات سائلة وأجزاء نفايات صلبة، وإيش المحتويات منها في كل وحدة، الأخطار البيولوجية، الأخطار الكيميائية، الأخطار الفيزيائية. المياه المعالجة ليش حكينا أنها كنز؟ لأنه 99% من المياه هو ماء، 1% هو مواد صلبة. فنتخيل قديش حجم المياه المتوفر من إذا كان في تفعيل إعادة الاستخدام أو معالجة المياه. ال1% فيه مواد غير عضوية اللي هي أملاح ومعادن ورواسب، و70% فيها بروتينات وكربوهيدرات ودهون. ليش الأسباب اللي احنا نبحث عنها؟ إنه احنا لازم نروح لإعادة الاستخدام، لازم نفعل إعادة الاستخدام، محدودية الموارد المائية الموجودة، الكلايمت تشينج اللي احنا بنواجهه الآن بالأردن، التغير المناخي، تغير نمط الأمطار اللي موجود، يعني معظم تحدياتنا هي واقع وملموس. فعشان هيك المزارع ولا المواطن الأردني راح باتجاه الاستثمار في إعادة الاستخدام. إذا نظرنا لها بنظرة يعني environment، فهي أنا الصورة على فكرة هاي كلها تترى على فكرة من الأردن، كلها من محطات، من مواقع مجاورة لمحطات التنقية أو محطات المعالجة. إذا نظرنا لها نظرة بيئية، فصار عندي إعادة للحياة البيئية على طول، يعني مجرى السيل الزرقاء، على المحطات اللي محطة العقبة فيها مرصد الطيور، على إنها غنية أصلا هي بالنيوترينت والمفيدة للنباتات. ممكن نطلع منها الآن الخربة السمراء، يعني عندهم مشروع تقريبا هم 90% إلى 95% من استخداماتهم الطاقة جاية من عمل ذاتي. الآن في توربينات على مدخل المحطة وفي توربينات على مخرج المحطة بيولدوا منها طاقة، يعني فيها استثمار عالي، فيها الانرجي اللي هو الكومبايند هيت باور، فيها السوج غاز. وإيش استثمار الآن إحنا مثلا في مكب النفايات بالغباوي، في استثمار عالي جدا في غاز إنتاج غاز الميثان. في الدول الثانية كلها الآن تصدر منها طاقة تروح على الغاز جريد. السوج سلج، الأردن تقريبا إحنا ننتج 105,000 طن من السلج، ممكن استخداماتها وممكن تزيد كمان بال2050 راح تزيد عندنا كميات كبيرة. فلحد الآن في عندنا محددات لاستخدامها، ممكن نستخدمها بالسماد، ممكن نستخدمها في إنتاج الطاقة. المصانع اللي موجودة الآن الديسنترلايز، احنا في توجه على المصانع الآن كل المصانع تستخدم المياه الخارجة منها بعد معالجتها ضمن المواصفات الأردنية المطابقة لها. يعني الجوردن ستاندرز، المواصفة الأردنية 893 على 2021، طبقت يعني المعايير الجودة في منظمة الصحة العالمية على COD والBOD والإيشيا أوكولايا. بالوقت الحالي الآن احنا في يعني تقريبا إذا تلاحظوا في الستاندرز للديسشارج الووتر، كل المحطات الموجودة 29 محطة مطابقة لهذه المواصفات. في 4 كاتيجوريز لاستخدام الستاندرز لاستخدام المياه، في على الباركس، في على الفروت، في على الفودرز، في على الفلاورز، ونشوف كل المحددات الموجودة هاي واحنا متقيدين فيها وملتزمين فيها، وفي عندنا رقابة وجهات رقابية عليها من وزارة البيئة ومن وزارة الصحة مع المجتمع. 29 محطة أكبر قلنا الخربة السمراء، كل وحدة في لها استخدامات معينة، قديش الكمية الناتجة منها والكمية الخارجة منها، قديش الكمية وين تروح بآخر شيء تنزل فيه المي واستخداماتها. بنشوف إحنا بالأردن تقريبا 77% إذا نحكي عن الزراعات هي زراعات مقيدة تقريبا، يعني الألفا والشعير والذرة زراعات مقيدة. في تقريبا في بارلي، في أوليفز. المحطات متوزعة بحسب الكثافة السكانية، 10 بالشمال وبالجنوب وبالوسط 12 وبالجنوب تقريبا 7. لا عفوا. الآن يعني إيش الكرنت سيتويشن الآن بالأردن؟ إحنا 92% من استخدام هذه المياه المعالجة اللي 215 مليون متر مكعب. أنا كنت أفكر 7% اللي ظلن أو 8% اللي ظلن إنه ما في لهن أي استخدام. بالعكس، لما كنت أنا مديرية البيئة رحت على المحطات اللي بتصرف على الأودية، لقيت إنه 8% هاي الموجودات المزارعين يستخدموها في الأودية، بس يعني خلينا نحكي خارج اتفاقيات مع وزارة المياه والري، فهي مستخدمة لحد الآن. أنا أتوقع أنها 100% يعني. زي حكينا كيف استخدام المياه المعالجة بالمحطات، في لها الدايركت يوزز اللي هي الاستخدام المباشر حول المحطة، وفي اندايركت يوزز بالأودية. اللي احنا يضبطنا في زي ما حكيت انه ايش المحطات هي دائمة ومتزايدة. نشوف يعني بال 2016 قديش كانت الكميات، لحد 2022 2023 كانت او 24 215 مليون متر مكعب. هذه الصور كلها على فكرة مشاريع تستخدم المياه المعالجة في محطات الموجودة عندنا بالأردن. الاتفاقيات بيننا وبين المزارعين، لأنه إحنا لحد الآن نحكي عن زراعات مقيدة، في اتفاقية بيننا وبين المزارع اللي يستخدم هذه المياه. الأغراض ليست تجارية ولا كانت تجارية. المتر يكلفنا تقريبا يعني في بعض المحطات نص دينار و70 قرش و80 قرش، إحنا نبيعه للمزارع للضبط لعملية القوننة يعني تقريبا بقرشين ونص المتر المكعب. فما مش عملية تجارية بقدر ما هي تحفيز للمزارع. هاي الاتفاقيات اللي بيننا وبين المزارعين، وهذه المناظر هذه كلها على إعادة الاستخدام. الآن المساحات الزراعية كلها في توسع عالي. حكيت المزارع الأردني الآن يعني مش شعر بالتغير المناخي، هو لمس التغير المناخي، شاف إن لما يستخدم المياه الجوفية قديش تكلفة الطاقة في إنتاجها، قديش المردود منها. لما راح على الزراعة على الريوز شاف إنه فيها مرابح عالية جدا، فيها يعني الانبوت فيها قليل. الووتر كواليتي إلها يعني عالية جدا. البارامترز اللي حكيناها احنا المواصفة الفنية 893 على 2021 في الفور كاتيجوريز اللي الفروت واللاندسكيب والفلاورز يعني عالية منطبقة فيها. هذا مرصد الطيور بالعقبة، قلنا انفايرمنت يعني شيء بين محطة تنقية العقبة الميكانيكية ومركز رصد الطيور. احنا طريق لهجرة الطيور، فما كان عندهم المياه، اخذوا من المحطة وصارت يعني الآن الزيارة ويعملوا عليها زيارات رسمية. المزارع اللي موجودة عندنا بالرمثة زرعوا على الذرة بالري بالتنقيط، كان ما شاء الله ناجح جدا يعني. بس أنا حبيت يعني الCOD والBOD والTDS عليهن، وكلهن يعني أغلبية يعني خلينا نحكي 90% موافقات للمواصفة الفنية اللي احنا شغالين عليها. زي ما قلت لك المزارع الأردني يعني بيفخر إنه بينتج رغم التحديات هي، هو رغم ما زال ينتج وما زال يعني واقف على رجليه. السعر يعني مش لوزارة المياه أنا بحكي، بس إنه أي مواطن بيشوف إنه السعر مش تجاري. إذا يكلفنا 29 قرش بالسمرة، بالجنوب عمان 25، بمعان 91، ونبيعه قول بقرشين ونص، بقرشين ونص المتر المكعب خلال فترة تشجيعيا، خلال فترة شهر 11 12 1 و2 مجانيا. بس خذ المياه يعني واستخدمها أو احفظها عندك في المزرعة. في احنا تحديات وفي يعني معيقات وفي تكاليف الانتاج، تكاليف التوزيع، ديستريبيوشن للمياه المعالجه. الكل يفكر انه بس الزراعه اللي يعني اندايركت يوزز اللي هي حول المحطه، بالعكس احنا في منطقه جنوب عمان تقريبا ضخ 14 الى 15 كيلو بعد المحطه، فهذا بيكلفنا طاقه وفيها يعني ايش الجفرمنت كيز اوبجكتيف اسوشيتد تو ووتر مانجمنت، يعني في لازم يكون في سستينبل، لازم يكون في بابليك انفايرمنت، في يعني كوبينج وذ ووتر سكيرسيتي، امبروفينج كواليتي، امبروف ووتر سيرفيس. كلها يعني ايش المشاكل اللي احنا لا يعني ايش يعني المشاكل اللي احنا واجهناها، شو بدنا نعمل لها عشان مثلا نقلل هذا التحدي او نقلل هاي. يعني لازم نروح لديسيلينيشن، ريوز، نحسن المحطات. ممكن في عندنا شيء مستقبلي أن يكون محطات التنقية الموجودة منتشرة بالمملكة بتكون في هاي الشبكة كلها توزيعات للمياه المعالجة. نأمل إن شاء الله بال2040 إنه إحنا بنزيد نقلل السيرفيس ووتر والجراوند ووتر باستخدام الزراعة، ونزيد الكريم ووتر، وبالكمان بالصناعي استخداماتها كثيرة وشغلها. يعني أنا آسف عشان الوقت. الحصاد المائي، استخدام التكنولوجيا الزراعية في الإريجيشن، هذا المركز الوطني للبحوث الزراعية استخدم دريب إريجيشن أو صب سيرفيس إريجيشن في المياه المعالجة، وكانت ناجحة عنده إنتاجية الدلم، وهم اللي طوروا الجهاز اللي يعملها. التفكير انه نروح ما نروح يعني بدنا نحكي نروح على فيرتيكال اجريكلتشر اللي هي الزراعه العموديه، استخدام كفاءه المياه لانتاج اعلى يعني انتاج باقل كميه مياه. المناظر اللي شايفينها انتم هاي موجوده على محطاتنا، حياه بيئيه، حياه زراعيه، يعني مشاريع زراعيه فيها. وشكرا لكم. انا اسف اديت الوقت.
مشكور دكتور، مشكورين جميعا. يعني صح الوقت ضيق، لكن رح ناخذ شوية دقائق لبعض الأسئلة. بس إذا سمحتوا لي سؤال، هل باعتقادك القرشين ونص هم أحد أسباب إنه المزارع تشجع على الزراعة في الأردن؟
يعني أنا قلت لك هو المزارع لمس التغير المناخي. المزارع لمس التغير المناخي، غير هيك فيها فرصة استثمارية. الآن إذا المتر المياه الجوفية بكلفه 70 قرش أو 80 قرش وفي بديل آخر، مع قصة نجاح، هو لما جرب ما جرب على مساحات شاسعة، جرب على مساحات صغيرة، شاف إنه فيها قصة نجاح، شاف في تسويق لمنتجه، وما شاء الله الآن يعني إحنا مش ملحقين على طلبات المياه.
إن شاء الله. بدي أخذ أسئلة من حضور إذا سمحتوا. تفضل.
First of all, thank you very much for all panelists for the interesting presentations. But I have a question for Ms. Hiba. What I understood from your presentation that FAO is promoting decentralized desalination plants for the agricultural purposes. But I think, as you know, most of the farmers are non-educated and illiterate, and it will be very difficult for them to operate such a desalination plant in their farm. So I think this should be taken into consideration when we want to promote any decentralized desalination plants. Especially it's very expensive plants. We are not talking about a cheap unit. Otherwise, maybe we have to think about fully automated desalination plants. In this case, the farmer has to only switch on or switch off the plant, and that's it. What about also including the centralized desalination plants for agricultural purposes? Do you think this could be an option in order to not increase the risk of failures of operating the desalination plants?
Thank you. دكتور محمد سؤالك. ناخذ بس كلمة سؤال.
شكرا جزيلا. أنا اسمي محمد الحمدي من الFAO. I have a question. I have actually several questions, but the main question is to Dr. Qadayshat. You mentioned new technologies, membrane distillation and forward osmosis, but you didn't show, or maybe I missed it, the cost element of it. If it's so attractive in terms of cost, why hasn't it picked up? Because usually the market is quick to pick up these opportunities. Another small question for Ms. Pauline. You mentioned that to produce one car in Morocco, it consumes 1 cubic meter. This is astonishing to me. Does this include all the parts that are coming from different suppliers, or is it just in the so that's not really how much water is the virtual water of a car is not 1 cubic meter. It's much more than those if you consider all the supplies that come from the different suppliers. Thank you. Maybe another question, Ustad Tawfiq. You've mentioned the cost, and we see that there is في فرق كبير بين الكوست ومن في المحطات المختلفة. ايش السبب في هذا؟ هذا واحد. والشيء الثاني لما بتكلم انت على الكوست، هذه تكلفة المعالجة، هل المواطن بيدفع مع فاتورة المي كمان للسيرفيس للسانيتيشن سيرفيس in the tariff? Do you recover the cost of treatment من الفواتير المي ولا لا؟ شكرا.
سؤالك لو سمحتي تفضلي.
يعطيكم العافية جميعا. اسمي رنا عارضة، الجمعية العلمية الملكية. أنا عندي كومنت على الكومنت تبع الأستاذ. إحنا مزارعنا اليوم at least in Jordan is very and highly educated صراحة. And بتتفاجأ قديش هم بيعرفوا معلومات. I'm sorry, I'm going to speak in English. Our farmers, particularly in Jordan, are really highly educated, and you get surprised when you talk to them and when you get to engage them in your projects and in your activities, how experienced they are. They just lack some kind of guidance, and I think that it's unfair to say that farmers are not educated because we've been working in the field extensively, like since 20 years, and we've been in contact directly with farmers. Farmers are really, they are not used to change. They are hard to change. You have to work on convincing them. but it's unfair to say that they are uneducated. Most of them are agricultural engineers, and if they weren't engineers, they get services from engineers, and they try to get guidance as much as they can. So this is the only comment I have. Thank you.
Thank you. Says Ashtaz.
Okay, thank you very much. My question to Dr. Tishat related to the distillation membrane technology that's you innovated, and in relation to the temperature, what the maximum temperature you reached without, collapsing the membrane itself. The second, it's a clarification related to the farmers and desalination, which mentioned by my colleague, Dr. Mu'tasim. Actually, we had a project which is called Smart Farm. It's financed by GIZ in Gaza before the war, and it was between 2020 until 2023. And we had a very successful outcomes. We installed smart irrigation systems in addition to the desalination plants. And the feasibility of desalination of brackish water, it depends on the area and the need, the cost as well of the alternative water there. So maybe it's applied in Gaza, not applied in another area. So that's why, but it was in Gaza in certain areas, it was most feasible, and people or farmers started to copy from that pilot project from GIZ and financing desalination plants from their pockets. And was very successful. And I think later on, FAO started to copy from GIZ as well in Gaza in 2022. But then the war came, and now...
Thank you. Thank you.
Thank you.
Final question.
Thank you. Laurent Poiret, Veolia, Jordan, on Lebanon and Egypt. Just a comment on the question. Each time I visit Jordan, I'm amazed when I am in Samra, when I am in Petra, when I see the south, the reuse on what Jordan has been able to do with the reuse of water for agriculture, for instance. And I have a question. When do we start? I think what Pauline has explained is the circularity concept. And Jordan, which was a pioneer to use the water twice, when do we use more than twice the water? I explain myself. We have someone from Daom behind, so DZ Amman operation and maintenance. We bring the water from DZ to Amman, then it's consumed in Amman and it's recycled in Samra after for agriculture. We use the water twice, but with the circularity that Pauline has shown on the Tanger example or Namibia example, we can use it much more than twice. And we invite in Veolia whoever wants to see Tanger or Namibia's example.
Thank you. Hiba.
Yes, thank you for the question. Actually, FAO is not trying to promote decentralized plants at all. Actually, what we're trying to say is that for desalination for agriculture to be cost efficient and to be profitable, it needs actually to be integrated within the larger strategies of integrated water resources management that is done by the country. And this requires looking at the trade-offs, looking at the best locations that these plants need to be done, the feasibility studies, a comparative analysis, or from where to supply and what is the best options in the intakes, in the disposal, etc. So the decentralization is not what we're trying to promote here at all. With respect particularly also to the capacity of farmers, as I mentioned, each feasibility study needs to be taken by its own, but one of the main pillars, as you mentioned, it needs to be the comprehensive socio-economic analysis that needs to be done. We need to properly understand the communities that are being introduced to these new technologies, understand their capacities, their needs, the economic benefits that would return onto these communities, and accordingly plan the overall plans for desalination. And we've seen this, this is the examples, the successful examples, but maybe I didn't have the chance to go through case studies in details, but in the publication you will find that the successful examples in Spain, in Morocco, in Malta that looks promising actually followed this approach, the integration of the desalination within the broader scope of the country's integrated water resources management strategies.
Thank you. Professor?
Thank you. I have two questions mainly. Professor Hamdi
Still
asked...
2 minutes only.
Huh?
2 minutes only.
Yeah, I'll just answer quickly. Asked about the cost associated with these technologies. I have made some calculations for membrane distillation specifically. It's the cost of 1 cubic meter is around 52 cents per cubic meter. That's for a capacity of 1,000 cubic meter per day. If you compare that to RO is higher when the capacity is lower. So I always believe, commenting on the I am a big fan of decentralization of desalination, especially in Jordan, because we have a lot of brackish water that is saline and the salinity level varies from one place to another. In addition, we have some water that comes with a little bit of hot water, like 50 degrees Celsius or 60 degrees Celsius. So to do it with RO, you need to cool it and then send it to the RO membrane. And that leads me to answer your questions about the thermal stability of the membrane. Opposite to the RO membrane, our membrane is much more thermally stable because we use aluminum oxide as a main layer, so it's thermally stable. Another thing, the polymer we produce, the glass transition temperature of that polymer is above 230 degrees Celsius, so there is no risk for the thermal resistance as well as the chemical resistance of the membrane. I am a big fan of decentralized desalination, especially in Jordan, because I do believe that could answer our problems and solve our problems.
Thank you.
I liked what Dr. Hazem said about the water reuse, and I share the same question with Professor Hamdi, why there is prices fluctuation from an area to another. Thank you very much.
Pauline?
I think it was more or less answered already, but yeah, when we are talking about 2 meter cube per car, it was what was used in the plant itself, so it's not taking into account the full equation of the production. But on site, it's reduced by from 2 to 1, and overall, on the other component, etc., it's been reducing by 70% the water consumption of the site itself.
Thank you. Doctor?
الكوست المرتفع للمحطات يعتمد على طبوغرافية المنطقة. الآن إذا شفتوا الخربة السمراء تقريبا 23 قرش، المعان أو وادي موسى تقريبا 90. بعدها عن المكان محطات الرفع اللي نستخدمها ما تكون نقل المياه باي جرافيتي، الكثافة السكانية الموجودة كل ما قلت الكثافة السكانية كل أصلا ما زادت التكلفة. فطبوغرافية المنطقة، وأصلا إحنا طبوغرافيتنا بالأردن طبوغرافية يعني جبلية فيها محطات رفع كثيرة لما ننشأ خطوط الصرف الصحي. كمان في شيء ثاني اللي هو التقنيه المستخدمه داخل محطه التنقيه، اللي تكون شو نوع التقنيه، هي تريكينج فلترز ولا اكتيفيتد سلج ولا، فهذا حسب الكونسيوم للطاقه يعني بتكون محسوبه فيها. الان هل المواطن انه يدفع فيه يعني بدلات الريوز؟ ما بيدفع هو المواطن، لانه احنا اصلا هو بيدفع رسوم للاشتراك للتخلص من المياه المنزليه الصرف الصحي، هذه تروح بانشاء الخطوط ومحطات الرفع لما تصل عند المحطه هناك بتعالج وبعدين بتطلعها. لو انعكس كان لازم انا ابيعه مثلا 90 قرش بمعان، ابيعه بالخربه السمراء ب 23 قرش، بس احنا ما بنعكسها لانه شيء يعني خاص، هو تشجيعيه للمواطن انه عشان استغلال واحلال المياه المعالجه بالمياه الجوفيه.
Thank you. Well, frankly, these were among the best presentations I've seen so far. So thank you very much, all of you. And dear audience, thank you very much. It was really fruitful. Thank you all. We have only 10 minutes for the next session here. Thank you.